Hello everyone. Welcome to my channel. Today, I will introduce you an excellent paper named An Analytical Framework for Modeling Ride, Pooling Efficiency and Minimum Fleet Size, whose author is Stefan M.H.L.E. First of all, I will show you the abstract of this paper. Ride pooling is a transport mode using on-demand buses to combine the trips of multiple users into one vehicle. Its required fleet size and carbon emissions are quantified by the system's efficiency due to the complex interplay between street network, buses, users, and dispatch algorithm. Efficiency case studies are available, but bottom-up predictions are not. Here we close this gap using probabilistic and geometric arguments in an analytical model framework. Its modular design allows for adaptation to specific usage scenarios and provides an overarching view of them. In a showcase on Euclidean spaces, our model quantifies how our P outperforms private cars as user demand increases. Its predicted power loss scaling is verified using a custom simulation framework, which further reveals improved scaling on real street networks and graphs with hierarchical structures. Henceforth, our work may help to identify street networks well suited for our P and predict key performance indicators analytically. Secondly, I will introduce the flow chart. To begin with, basics are consisted of the 8 parts, including paradigm and notation, bus status, bus occupancy, detour factor, demand, supply-demand balance, efficiency and minimum fleet problem. What's more, this paper proposed a generic, modular modeling framework with the goal of obtaining an analytical expression for data. It does not rely on simulation results, but only on ingredients required to start one. Chapter 5 and 6 are the application of model framework and simulations. In a nutshell, this paper conjectures 3 major regimes of our P efficiency and fleet size scaling. Fully occupied buses may be considered as a 4th regime, and presented a purely analytical model for our P efficiency, which is built upon a representative user's viewpoint. Next, we will concentrate on the efficiency model of this research. It does not rely on simulation results, but only on ingredients required to start one. The model's core idea is to consider the efficiency as it is experienced by a single RP user. The single user view's purpose is that it reduces finding data and solving the minimum fleet problem to modeling the probability distribution. M denotes the number of other requests being submitted during a time interval T0, representing our trip. K denotes the number of users we in fact meet on the bus. Hence the bus occupancy we experience is this equation. If M0, there is no other user we could meet on the bus, meaning K0, and thus PK0 K0. If M1, there is one other user whose request temporally overlaps with ours, and the question of whether we meet on the bus can be considered a geometric one, considering all M other users one at a time. With each of them the probability dist re, but I in PKM flows towards greater values of K. Following this logic, its evolution M playing the role of time is quantified by the following master equation. In summary, the workflow for applying the presented model framework is the following. 1. Specify map and spatial request pattern. Estimate overlap of shared routes X. Obtain mean route duration T0. 2. Specify user constraints. Geometrically model trajectory length growth delta K and insertion probability RK. 3. Choose dimension-less demand X, together with temporal request submission statistics. Obtain PM. 4. Solve master EQ. 20 iterative lie and obtain PKM. 5. Evaluate efficiency according to EQ. 18. 6. Using steps 3 to 5. Find pairs N. X that satisfy the supply-demand balance. 8. To solve the minimum fleet problem. Next is the application of model framework. This figure is the ellipse-based trajectory model. Stops are added to the journey from our pickup A to drop-off B. Ellipses define sets of all allowed extra stop sites, keeping total journey duration below a threshold, delta max. A. Our originally requested trip. With K0 other users met, there is no detour, and thus delta 01. B. Experiencing one extra stop at X incurs a mean detour delta. After that insertion, the allowed additional detour defines the width of the two ellipses between A and X, or X and B respectively. C. As more stops are added, the journey length delta K approaches delta max, and the allowed ellipses for the next stop insertion become increasingly slim. D. A simple heuristic for estimating the area of the union of overlapping ellipses around our trajectory top. Our route is flattened, preserving its length, such that a single ellipse round it can be considered bottom. These three equations make up the insertion probability. The second figure is model results. Furthermore, I will introduce the simulations. All data points use a dispatcher, which minimizes the total length of bus trajectories. A. Solutions to the minimum fleet problem on the map star grid 30 to 32. Shown are demands at which a given fleet size can serve 20, 40, 60 and 80% of all incoming requests respectively. After an initial regime that ends at around 10 buses, all curves are well approximated by a power law, with exponent 1.15. B. Various simulation observables, evaluated along the blue curve from Fig. A. Shown here in blue is the system detour delta system, which has the lower bound 1.0 and upper bound delta max to 0.0. As a consistency check, the served percentage of requests P except orange indeed coincides with the target value. 0.8 red horizontal line. The occupancy of driving buses B driving green grows unbounded, and is ultimately responsible for the power law behavior in Fig. A. The conditional probability, P occupied driving that a driving bus is occupied is shown in purple and approaches 1. Lastly, the fraction of time P driving that buses are driving, not idling, is shown in yellow and also approaches 1, but faster than P occupied driving does. See analogous curves to those in Fig. A for P except 0.8, but on different maps. The two star grids have aspect ratios 1 blue and 16 purple, but are identical otherwise, and show power laws with the same exponent. A higher aspect ratio of the map leads to a higher pre-factor of the power law. The green curve belongs to simulations on a real street network having an improved power law, exponent of 1.24. And the green curve refers to simulations on the map HT, REE for CA strongly hierarchical structure on which the other map's power law is outperformed. The blue curves in figures A and C are identical. The last part of this paper is the conclusions. The authors conjecture three major regimes of RP efficiency and fleet size scaling for low demand. Buses are idling part of the time, despite having to reject requests. Once buses are driving at virtually all times, the power law scaling takes over. The bus routes can no longer be considered to cover a negligible fraction of the overall graph. This paper presented a purely analytical model for RP efficiency, which is built upon a representative user's viewpoint. Central paradigm is the number of other users one may expect to meet on the bus, and how this affects the trade-off between bus occupancy and incurred detours. Finally, they suggest three directions for future work. Firstly, the model framework should be supplemented with models for the probabilities P occupied driving and P driving. Secondly, Explicit expressions for the trajectory length delta k and insertion probability rk should be sought for maps other than areas on the Euclidean plane. Linking the efficiency S scaling behavior to the map S topology directly. Thirdly, systematic simulations on simple rectangular maps should be run with state-of-the-art optimization techniques in order to investigate whether or not our Model S predicted scaling behavior can be improved upon by means of the dispatch algorithm alone.